Okay, so exponentials. This is the second half of our week in regards to sequences. What you're going to find is that an exponential function is very much like a geometric sequence. So here's some definitions. If you need to pause and copy them down, that would be helpful, but they will help us during our conversation about exponentials. First, let's just talk about what the equations look like. Like I said a minute ago, the equation looks just like a geometric sequence. So we're going to have A, or initial value. We're going to have B, which is the multiplier, and our variable is still x. So we're basically taking a geometric sequence now and applying it to a function. So the first example we're going to do is to write an exponential function for each situation. Now when you're reading these examples, right, what we need to do is rely on the definitions on the previous page and also try to interpret from the example what the initial value is and either what the multiplier is or how we get the multiplier. So in this first example, we purchased a house for $120,000 because that's what you purchased it for and that's what it's worth. That is our initial value. Now the only number provided to us is an interest rate of 5.3%. We're going to use that to find our multiplier. So in the previous page, we talked about some definitions there, and percent increase is defined as 1 plus the percentage. Okay, so 5.3% would be 0.053. 0.053. That will be your multiplier. Now you can add them together. 1.053 is our multiplier. And $120,000 is our initial value. So if I write the function, I will have y equals 120,000, 1.053 to the x power. So again, initial value, multiplier. The difference here compared to the geometric sequences we worked with yesterday is that you have to find the multiplier. It's not given to you in the problem all the time. Part B, we opened a savings account with $1,500. And the interest rate of that savings account is 2.2%. So because the $1,500 is what we deposited, that's our initial value. The interest rate in a savings account grows, so we're going to 1 plus 0.022. Now if you're unsure about that, changing a percent to a decimal, all we're doing is dividing by 100. So I'm getting that 0.022 by taking the percent divided by 100. Percent divided by 100. That should be something we've seen before. When I add those together, I get 1.022. Multiplier. Initial value. Y equals 1,500. 1.022 x power. Next, we have an example of a decreasing exponential function. And the way we know that is by the word depreciating. That was in your definition list. You need to be able to recognize some of these words. So we own a car worth 25 grand. That would be our initial value because that's what the car is worth right now. It is decreasing in value at a rate of 11%. If it is a decrease, we're going to take 1 minus our percent, 0.11. Again, that decimal comes from taking the percent divided by 100. 1 minus 0.11 gives me 0.89. That's my multiplier. This is my initial value. My car is going to be $25,000. What it's worth when I drove it off the lot, 0.88 to the x power. Letter D, a sample of bacteria numbering 1 times 10 to the 5th is doubling every hour. So the wording here is a little bit different. Okay, we're talking about a sample of bacteria numbering 1 times 10 to the 5th. That's scientific notation. You can leave it in scientific notation if you'd like. You can move the decimal 5 times and write it as a number if you'd like. But this would be the initial value because that's how much. Now, what is happening to it? It is doubling. So we're using, some word recognition here. If it is doubling every hour, okay, then that means our multiplier is going to be times 2. So my equation is going to say y equals 1 times 10 to the 5th is my initial value. My multiplier is 2 because it's doubling to the x power. So we got to be able to recognize some of these keywords: doubling, tripling, quadrupling, things like that. Those words we would need to know: times 2, times 3, times 4, whatever they mean. Here we're going to define x as an hour. Letter E is the trickiest one that we have here. This is something you'll see in science class if you haven't already. It's something we're going to talk about in the Penny Lab. The half-life of a 30-gram sample. So 30 grams is an amount, that's our initial value, of bromine 85 is 15 minutes. So we have a couple things going on here. All right, the 15 minutes is going to be important. That means it happens once every 15 minutes. That means that 30 grams decreases by half. That should tell you what your multiplier is. And that happens every 15 minutes. So if we were going to write our equation in terms of hours, how many times in an hour is this happening? There's 4 15 minutes in an hour. So my equation is going to say y equals 30 grams. Because it's half-life, the multiplier is always 1/2. Now the exponent's a little tricky. If x is hours, okay, and this is happening 4 times per hour, I would have to say 4x for my exponent, because it happens more than once an hour. It happens 4 times an hour. And that would be my equation for half-life. So writing the equations is one step. E is the hardest one. That's a team test question. That's a bonus question. A through D, though, those are ones that you're going to have to be able to do. Example 2. Here we want to state whether the function represents exponential growth, decay, or neither. If it's exponential growth or decay, state the rate or percent of growth or decay. The way we're recognizing that is x. So, okay, state whether it's exponential growth, decay, or neither. Is x the exponent? If it is, it's exponential. So that's the question you have to ask yourself, the question you have to answer. All right, now, what the rate or percent of growth decay is, we're looking at the multiplier. If it's greater than 1, it's growth. If it's less than 1, it's decay. So when I look at this first example here, all right, x is the exponent. So yes, exponential bigger than 1, the multiplier is greater than 1, growth. Okay, how much bigger than 1 is it? It's 0.25 bigger, which is 25%. Second example, x is the exponent. Yes, exponential. The multiplier is less than 1. That tells me it's decay. It's going to decrease. And then what is that difference? The decay rate is not 0.88. Okay? The decay rate is the difference between the multiplier and the number 1. So it's decaying by 12%. So basically you're asking yourself, how much do I have to add or subtract to this to get to 1? And that's how I come up with that number. Next one, is x the exponent here? No, neither. And finally, is x the exponent? Yes. Is my multiplier bigger than 1? Growth. And how much bigger than 1 is it? 0.025 as a percent is 2.5%. Now an example problem. Tony invested $1,200 in an account that accrues 5% annual interest. So just like our first example, we're going to determine these pieces. What is the initial value? The initial value is how much he invested, $1,200. What is the multiplier? We're going to use the percent to get the multiplier. That's percent growth. So 1 plus 0.05. And again, I'm taking that 5 divided by 100 to get 0.05. Write my function. So y is going to equal 1,200 times 1.05 to the x power. Answer the question. How much money will Tony have in the account after 15 years? So the 15 is what goes in for the X. These are great lessons, okay, for as you get older, how to invest your money, how to save your money. So y equals 1200, 1.05 to the 15th power. Make sure you use the caret key on your calculator for that 15th power. And if I type that in, I get y equals $2,494.72. So Tony gained whatever that number minus 1200 is. He gained basically $1,294. So he doubled his money in 15 years. Now, that's not a lot, but it's more than he started with. Last example, this would be the challenge. Okay, this would be the challenge example. This would be the bonus. Darren invests $5,000 in a savings account that has 3% annual interest, compounded monthly. That was in your definitions. You need to know what that means. Great team test question. $5,000 initial value. The multiplier. This is going to be a little more difficult now because this 3%, 3 divided by 100, is 0.03, but it's being compounded monthly. Okay, so how many months are in a year? 12. So I have to take that number divided by 12. Okay, so 0.03 divided by 12 gives me 0.0025. It is increasing, so I add 1 to it, 1 plus 0.0025. That's my multiplier. I write my equation, y equals 5,000, 1.0025, but my exponent is different. X would be once a year. This is not happening once a year. This is happening monthly. So how many times per year is it happening? It's happening 12 times per year. So 12x is my exponent. How much money will Darren have in the account after 10 years? I plug 10 into my equation. Make sure if you type this in the calculator, you group the exponent, unless you calculate it in your head first to be 120. You're going to need a calculator for these. And Darren has $6,746.77 after 10 years of his investment. This is the challenge problem. This is not an individual test question. This will be a team test question.